Okay, let's get started here. So project number 3 is due on Friday at noon. Test number 3 is Wednesday, December 4th. Are there any questions? Okay, so we left off last time on page 40 of the notes. Oops. Now, if you've taken I guess a good course on regression analysis, generalized linear models, such as Stat 870, Stat 875, you know, a central focus of those courses is to determine what variables to include in your regression model. The reason being is because you want to be able to interpret these variables and their effect on the response variable. Now, when we're trying to predict the population that an observation comes from, such as using discriminant analysis methods and also using other methods that we will continue talking about for the rest of the semester, we aren't really concerned about what the effect of a particular variable, we're not really concerned about the effect that a particular variable has on whether or not this observation is from population 1 or from population number 2. So because of that, are you looking for your cell phone?
Yeah.
Was it kind of was it Apple?
iPhone.
Yeah, I gave it to Kathy. Kathy Hanford, your teacher?
Oh, my teacher?
Yes.
Oh, thank you.
Yeah. Anyway, maybe more instructors should go by their first name so that students know who I'm talking about. Anyway, again, please call me Chris. Don't call me Dr. Billner. Please call me Chris. Anyway, so we were talking about with discriminant analysis, we're really not concerned about understanding the effect a particular variable has on whether or not this observation comes from population 1 or comes from population number 2. And so because of that, you find in multivariate analysis books very little discussion about variable selection to determine, well, which variables are you going to use. So again, let's say if you have 10 variables in your data set, variable selection then looks at, well, which of these variables are really important to help you differentiate between the different populations. And so again, typically this topic's not discussed a whole lot. And, you know, excuse me. Let me look at my notes so I make sure I'm talking about everything I want to. And, you know, I would say also, you know, at most you would do only a little bit worse if you, let's say, you included a variable that really wasn't important in your discriminant analysis. And the reason why I say maybe a little bit worse is that for every parameter that you're estimating, you're inducing a little bit more variability in your methods that you're looking at. And more variability then could affect the overall correct classification rate. It probably, for a variable that is not very meaningful, it's probably not going to affect it a whole lot, but it could. So you might be thinking, well, maybe still it might be worthwhile to look at variable selection. And actually, Dallas Johnson in his 1998 book does do that. And I've actually talked about variable selection every time that I taught this course previously, but I've decided to change things and not actually talk about it. And here's why. While it might be nice to say that I only need to have, let's say, 2 variables versus 10 variables throughout the entire that are in your entire data set, because, you know, if you only have 2 variables, obviously then you have less information that you have to collect data on in the future. And also, if you only have 2 variables, you'd probably be able to view what's going on graphically a lot better than if you had 10 variables. So, you know, there is some benefits from it. But the problem is that, you know, for those of you taking Stat 870 and you've taken Stat 875, you know, how do you do variable selection? Well, there's typically 2 different ways. Hypothesis tests. and using a Keki's information criteria or other similar AIC-like methods. But none of those methods really get at the core of what we're interested in here, and that is to look at the correct classification rate. You know, your classification actually, they don't measure that at all. So to some respect, if you use hypothesis tests, if you use AIC to help judge which variables to include in your discriminant analysis method, you're not actually looking at the right criteria. And so you might think, well, why don't we just look at the correct classification rate? Well, let's say if you have p variables. How many different possible models could you have? 2 to the power p. So if you have, let's say, 10 variables in your data set, that's 2 to the 10. That's a lot of models that you have to look at and evaluate these correct classifications. So that's why, you know, it's typically not done. Anyway, though, the way that Dallas Johnson approaches it in his book is use what's called analysis of covariance models. If you had Stat 802, you've seen analysis of covariance models. I decided to leave the discussion in the notes about how he goes about doing that, just that if you wanted to explore it further, you can. But you are not responsible for it. There is a nice discussion, though, too, about why analysis of covariance models may not necessarily be the best choice in terms of determining which variables to include. In particular, plots on page 44 and page 45 really get at the heart of the problems with using, and Johnson uses this hypothesis test with analysis of covariance models. Okay, so that takes us then to page 47. Oops. And we have some additional comments about discriminant analysis that end this chapter here. In particular, you can do this stuff with more than 2 populations, and everything. And so far, we've only done 2 populations. If you do this stuff with more than 2 populations, and everything just works out fine. It's easiest to think about more than 2 populations using either Mahalanobis Distance or using the posterior probabilities. So, for example, with Mahalanobis Distance, let's say we have 3 populations, like you do in the project. And let me pull up my red pen here. With Mahalanobis Distance, you calculate the same way as we've done in the past. And let's say you get 3 distances. Well, in order to determine which population to classify a particular observation into, you look at 3 different distances. And let's say D2 represents the distance that the observation is from, let's say, population 2. Let's say D2 is the smallest. Well, then that means that you classify this observation into the population number 2. Very simple. If, let's say, that you use posterior probabilities, maybe you get for population 1, 0.4. For population 2, you get 0.49. And for population 3, maybe you get 0.11. Obviously, everything needs to add up to 1 here. In this case, again, you will classify the observation into population 2 because it has the highest posterior probability. So it's not really a big deal. If you were to use, let's say, the linear discriminant rule that we looked at the very beginning of the chapter, things become a little bit more difficult to work with. So that's why I don't think it's really worthwhile for us to look at it further when these distances and posterior probabilities are rather easy to extend to more than 2 populations. Okay. Now let's consider a situation where we have 3 populations, and I have a scatter plot of my data, and it's color-coded corresponding to the population that a particular observation comes from, and we only have 2 variables. Now, what one could do with discriminant analysis, I've kind of said this before with when we had just 2 populations, what one can do with discriminant analysis, and I don't think it's worthwhile for us to actually look at the math behind it, but what one can do is actually draw 3 lines, because you have 3 populations, draw 3 lines like this You could actually mathematically figure out what the best lines would be that would separate the different populations. One could do that. And the reason why I present this is because you can see a little bit what discriminant analysis does. It actually fits straight lines between your populations. It ultimately finds those lines that best separates the populations. And obviously that works very well in this situation. But let's say instead your data looks something like this. Again, the different colors represent the different populations. Now what I try to do is put the best 3 possible straight lines between those populations. But you can see here, I'm not going to have perfect classification. I'm not going to get everything right now. But you still see distinctions between the populations, and somehow you could actually, let's say, draw a line that looks like this. You know, you could still get 100% correct classification, right? Well, now you see then the problem with discriminant analysis, because it's basically focused on drawing straight lines between populations. And so you might think, well, maybe there's some kind of more flexible method out there, statistical method out there that doesn't draw the straight lines. And in fact, there is. And we will be looking at those coming up. Okay. Well, if you remember with the place-kicking data set, I told you that I collected about 1,700 observations, and before I really started doing anything with the place-kicking data set, I basically pulled 20% of the observations randomly out of my data set, put them aside, and then used the remaining 1,400 or so observations to basically find the best discriminant analysis method for it. Well, how do you actually do that? If you haven't seen how to do something like this before, that's the purpose of this next discussion. Let me turn off my spell check here. Hold on a second. Make sure I am recording. Yeah. Okay. So, again, what I want to do is randomly split, let's say, a data set that has 1,700 observations, randomly split it into a what you call a model building, you can call it training, or you can call it my original data set. That having 80% of my observations, and then also have a data set that's called my validation, also called calibration, also called like a test data set. This other data set has 20% of my observations, and I want to randomly split it in an 80-20% mix. Why would I want to randomly split it? Why don't I just take the last 20% of my observations? I think what you're getting at is that the order could matter, and that perhaps, and the way that stuff is organized in the data set right now is at the end of the season is the last 20%, and so perhaps by then the place kickers are kind of tired, and maybe they won't perform as well. The grand scheme of things is not just in a place kicking data set. You don't want any kind of bias to be introduced into your analysis by not randomly, choosing observations to put into the validation data set and randomly choosing observations that will go into your model building data set. You don't want to introduce any kind of bias. So that's why we do this at random. And there are 2 different ways I'm going to show you how to do it. First of all, though, what I would like to do is put if you remember before, we had a data frame called PlaceKick. That was the model building training data. We also had a data frame called Valid, which was my validation data set. I'm going to put them all together into one overall data set to simulate what we would have actually done in practice if I hadn't actually given to you the split data. And so the way that I can basically take my PlaceKick data set and put my validation data set right below it is to use a function called rbind, row combine. That's where the name comes from. I'm going to do that. Oops. There we go. And we can see that I have 1,700 observations in it. Okay, so method number 1. I guess actually with both methods I have to do this first part. What I'm going to do is generate 1,700 random observations from a uniform 0-1 distribution. Now, all of you should have seen a uniform distribution before in your very first stat course. Here's just a brief review. Here's my random variable. I'm just going to call it U. And we're going to have a uniform distribution between 0 and 1. And simply, when I draw out the distribution itself, it's simply what should be a horizontal line. I can't draw very well. From 0 to 1. What this basically means is that the probability of being between any equally spaced interval is exactly the same. So the probability that a random variable is somewhere between, let's say, 0.05 and 0.1 is exactly the same as between 0.95 and 1. Okay? And so what I'm going to do is generate, corresponding to my data, my original data set size of 1,700 or so, I'm going to generate 1,700 uniform observations, randomly generated. And so to do that, I'm going to set a seed so I can reproduce what my results are. The function to do the random number generations are unif. Sample size n.all, that's what was coming from here. Bottom number is 0, top number is 1, and we're going to look at the first 6 by default. So the first one is 0.014, the next one is 0.078, and so on. And so what I'm going to basically do is assign these random numbers to each of the observations. So my first observation, my data set is going to be assigned a value of 0.014, second observation 0.078, and so on. This is going to help me to split the data. Okay. So, excuse me. First of all, I need to figure out, well, how many observations would go into my training data, my model building data set, if I had 80% of the observations in there. So I create an object called cutoff. And I take 1707 times 0.8, and I get 1365 point something. Obviously, we can't have, I'll just show you what the actual value is. We can't have 0.6 of an observation in a data set, so I use the floor function to simply chop off the stuff after the decimal place. So I'm going to try to put 1,365 observations into the training data set, and then we will have in the validation data set 342 observations. Okay. Now, what I'm going to do first is I'm going to try to rank all those uniform numbers. So again, we have 1,707 observations from a uniform distribution. I'm going to rank them all, meaning from smallest to largest. So for example, the 0.014 that we saw before is the 22nd smallest in the data set. 0.078 is the 146th smallest in the data set. This is all found with the rank function. And so what do you think is going to happen then when I use those numbers, those ranks, as the row numbers of my data set that has all the observations in it? What do you think is going to happen? You think the code's not going to work? And you'll get a syntax error? They're going to be basically randomly sorted. Okay? So the first observation that's going to be shown is number 22. The second observation will be number 146. So what that uniform number allows me to do is just simply randomly rearrange all my observations in the data set. That's it. So I'm going to put that into a data frame called all.data.reorder. And now, since everything has been randomly rearranged, how about we just simply pull the first 1,300 and, what is it? Oops. What is cut off? Yeah, 1,365. Let's just put the first 1,365 observations that's in this reordered data set. Let's just put that into the training and put the remaining observations into the validation. And that's all I do. So the first 1365 go into training. The next ones go into validation. And let's take a look at what happens. So 1,365 in the training, 342 in the validation. What's the percentage in the training? 79.96%. Again, right about 80%. That's what we're interested in. That's one way then that you can divide your data set into a model building and also a validation data set. Let's take a look at a different way. It's a little bit easier. The problem, though, is that you're not going to get as close. You may not get as close to the 80% like what we just did. Okay, remember all my uniform numbers are unif.split. And then I'm going to compare unif split with 0.8. Is it less than or equal to 0.8? So what's R going to return if I were to execute this segment of code highlight?
True or false?
Trues and falses. Okay. And then if I combine that then with essentially telling, let's pick off just the trues that are in all.data. And I'm going to put that into my training data set. Then, when unif split is greater than 0.8, put those into my validation data set. And let's see what happens. So I have 1,400 observations now in my training data set, and this represents 82% of my data. So notice I don't get 80%, but I'm kind of close. You know, if I were to write a paper, and if I was creating a model building or training data set and also a validation data set, I'd probably do it the first way because it's going to be easier to explain it in a paper that I put 80% in one data set versus 20% in the other data set, versus you saying, well, I generated uniform numbers, and you know, because of the variability in uniform numbers, I ended up with 82% and 18%. So I would have probably done it the first way in the paper, but you can see the second way is just a little bit easier. Okay. Are there any questions? Yes.
So for the first method, then like the rank function will replace the first column of the all data matrix or not?
Say that again, please.
Because the rank vector function will replace the first column of the all data or not?
I'm not replacing any columns in my data set. I'm only using essentially this ranking here to tell which row numbers to take. So while I've said that I've assigned, let's say, unif.split, I've assigned a uniform number to every single observations, I didn't actually put that in my data set. I didn't need to. Okay? All I need is essentially the ranks there to help me reorder stuff. Are there other questions? Okay, so if you hadn't seen doing something like this before, there you go. I know this is always a topic that I talk about, at least in my Stat 70 class, so for those of you who took that class from me, sorry to repeat myself. Lastly, on page 50 then, there's another topic that's sometimes talked about in multivariate courses when you're talking about discriminant analysis, and that's called canonical discriminant analysis. I've taught this course now 6 times, and I've taught canonical stuff about 3 times, and I doubt if I ever will teach it again, but I at least wanted to mention it to you because you might see other people use it. And simply imagine, let's say that you use principal component analysis first, and then apply regular old discriminant analysis to the principal component scores. To some respect, that's what canonical discriminant analysis does. With canonical discriminant analysis, what you do, first of all, you form what are called canonical variables. These canonical variables are very much like principal components in that the goal is that you want to reduce the dimensionality of your data. So that's what these canonical variables do. But they're chosen in a way to try to maximize, let's say, the differences between the different populations. Okay? And once you get these canonical variables, you get their scores, and then you apply regular old discriminant analysis to it. The advantage of using this particular method is that since you're maybe dealing with a lower number of variables, you can view what's happening with your data a little bit easier than maybe what we have done. It's maybe an advantage. I don't think it's really worthwhile because, again, we could just apply principal component analysis itself and view our data, or use some of these other graphical techniques to view our data as well. But if you're interested in knowing more about it, since I taught it before, you can take a look at my old Set 873 website when I used SAS, and you can see my description of it. So that's it then for those notes. I do want to tell you a brief story, though, before we move on to the next section. You may, or hopefully you do remember, me mentioning to you a particular situation that I had when I was on an internship at the Idaho National Laboratory, where I spent my summer trying to determine what's inside of a Sunny D juice container. Was it empty? Did it have juice? Did it have water? Or was it sand-filled? So I ran a lot of discriminant analysis methods on the data, and also other methods that we will talk about shortly on the data, to try to come up with a way to determine, can we differentiate between the different fill types. And what we found out, well, I would actually would help collect a data set of size 40. 10 sand, 10 water, 10 juice filled, 10 empty. And what we found out when we would apply like discriminant analysis to the data set and use cross-validation to get a measure of accuracy, what we found out is that this method, this procedure that we were using, worked very well. We have very good accuracy. So we were feeling good about ourselves. Then we decided, well, why don't we just go out and collect some more data? We can set up the experiment. It takes a few days to maybe collect the data. And we collect some more data. And so if you remember, one of the ways to judge how good your classification method is to go out and collect new data. That's actually the ideal method. So we did that. Then we applied the discriminant analysis method that we had just did. We applied it to this new data set, just like how we did with the holdout data set. And the results that we got back were quite poor. The method could not differentiate very well between the different fill types. We went out and collected another data set. Same thing happened. What do you think that's a sign of? Or why do you think that would happen in an experimental situation such as that? Interestingly, if I were to go out and try to find a new discriminant analysis method on one of these new data sets that I had just collected, run cross-validation on it, I get good results. But then when I apply those methods into a new data set again, it wouldn't work. Why do you think that's happening?
It is very specific to the data set that you gather.
Yeah, well, everything's very specific to the data set that I was gathering. That if I run cross-validation, it works. But then if I apply the exact same method then, to this new data set, it didn't work.
Different batch of plastic.
I think you're starting to get at the reason. I mean, they were different bottles. Yes, I remember having to actually go to the grocery store and pick up 40 Sunny D juice containers. I never expected that before I went out there during the summer, that I would be dealing with Sunny D. Didn't even drink Sunny D. Why do you think something like this would happen? Maybe think of a different situation. Maybe in your own research where you apply a particular statistical method to it, and it looks like it works. And then when you go out and do the ultimate test, where you apply the same statistical method, based upon maybe the mean vectors that you've already calculated, your covariance matrix that you've already calculated, apply it now to this new data set, and it doesn't work. What do you think what do you think the cause would be?
Probably the original data set is too perfect to have 10 sand and 10 water and empty. But for the other new data set, it's not range and base.
Well, it is arranged like that. We always made sure that we always had 10 of each. Okay.
Maybe you were missing other variables like temperature or something like that.
That could be it. You're kind of getting at it. You're missing stuff. What could I be missing? There wasn't actually other variables. There wasn't actually other variables that I could actually collect. but I think you're thinking the right way. I'm missing something. Do you want me to give you the answer? What's that? No, not. It wasn't the labels. They were all exactly right. It was the same type of label. You want me to give you the answer? Okay. The experiment's not being applied exactly the same. That was the problem. You know, whenever you go out and do an experiment, you're hoping to apply the experiment, or let's say apply, if you think of it in a set 802 set, apply treatment in exactly the same way. Okay? And what was happening is that we had some lack of control of how we were applying the experiment from, let's say, one run, or one, let's say, run of 40 containers versus another. I mean, a simple situation could be, this is maybe overly simplified, but I think you'll get the point. It's that, unfortunately, I didn't bring my Sunny D juice container today. Let's say that this is my Sunny D juice container. And what we would do is that we would set up, let's see how much it is. Okay, so this is a Sunny D juice container. This is a speaker. We would set up a speaker right here. We put the Sunny D juice container right here. We turn on some white noise from the speaker, blast it at this, and there was some kind of measure over here that would measure basically how the sound was coming through it. Okay? And that will give us an acoustic spectrum. Well, what happens, though, if maybe we put the Sunny D juice container a little bit closer? Do you think maybe the acoustic spectrum would be the same or different? Maybe a little bit different. And so we had a lack of control. We were not controlling everything from one set of experiments, one set of 40 observations to the next. We weren't applying everything exactly the same. And then that was in August, where we decided that was the reason. And I went home after that, my internship was over. So I did find out later on that they solved those issues, and they were getting a lot better results in the end. But the reason why I tell you this story is that, this is, again, example of real life. And, obviously we don't talk about those kinds of issues here. But I think it's an important issue to always think about whenever you're doing some kind of experimental setting. Okay, any questions? Okay, so let's move on to the next section. Nearest neighbor classification. Okay. So discriminant analysis is what's called a parametric method. If you haven't heard that term before, parametric that is, that's to mean that we are using some underlying distributional assumptions, such as a multivariate normal, and that's what was used to derive the method. There are also what are called nonparametric methods, meaning you are not using any kind of underlying distributional assumptions. Excuse me. Nearest neighbor classification is a nonparametric method. So there's less assumptions. And because of that, it can work a lot better than discriminant analysis if the underlying assumptions for discriminant analysis are not satisfied. Makes sense. If I don't have multivariate normal distributions, you might think that that's going to have some effect on the ultimate outcome. Fortunately, discriminant analysis is somewhat robust to non-normality, but still, there is some kind of effect. So you might think that some other method that doesn't have that assumption, in fact, doesn't have any kind of underlying assumption, might work better. And so that's what nearest neighbor classification is. It's quite intuitive, too. Here's how it works. Suppose I have 3 populations for my data. Population 1, 2, and 3. I have a nice little scatter plot here. I only have 2 variables that I collected information on, x1 and x2. And what we would like to do, let's say, is classify this red observation there. Classify it into either population 1, 2, or 3. And so it's somewhat intuitive to think, well, why don't we just look at similar observations to this red one? Well, what do I mean by similar? Well, in a plot like this, you can think of it as distance. Observations that are closest to the red one are more similar than observations that are farther away. So how about we look at the red dot's nearest neighbor? Well, its nearest neighbor is observation 1. I'm sorry, is this observation that comes from population number 1. Well, how about we classify that as coming, why don't we classify then the red dot as coming from population number 1? Simply how it works. Nearest neighbor classification. Very intuitive. Well, how about we go with the 3 nearest neighbors? Well, we could do that too. And so, based upon how I drew this plot, we see that the additional 2 neighbors come from population number 2. Since the proportion of observations from population 2 is larger than from 1 or from population 3, we classify the red dot into population number 2. How it works. This is called, in general then, let's say we could have capital K nearest neighbors, and so this is called K nearest neighbor classification. What if K was equal to 2?
Would be 1,
What?
like the population.
Why would you classify it into population number 1?
Well, you mean like the 2 closest
Okay.
neighbors?
Yeah, the 2 closest neighbors.
One is 2 and the other one is 1, right?
Yep.
Like on that graph.
Yeah.
But the 1 is closer.
Okay. What you've just done is talk about a different kind of nearest neighbor method. But let's just look at the 2 nearest neighbor. Yeah, as what we said. One comes from population 1, and another one comes from population number 2. Those are the 2 nearest neighbors. So if you just simply look at the proportion of observations from each population, we have a tie. So how do you solve that tie? There are a number of ways to do it. One way might be to look at, let's say, the closer of the nearest neighbor and classify it as population 1. Another way might be, let's say, to look at the next nearest neighbor, and then we get population 2 as the next nearest neighbor. So essentially you go to a 3rd nearest neighbor and classify the observation in population number 2. Another way would be to, let's say, randomly pick from 1 and 2, since there was a tie. And so you can see there's multiple ways that one can think of how to break the tie. Software packages are different. Some will do one way, some will do another. And so unfortunately, one of the more difficult things then in this section is to understand fully how R does it, how R breaks a tie. And we will talk about that. Otherwise, this section is fairly simple. So comments. We've already talked about the first one. The second one here. Obviously, distance is very important with this method. And so it makes sense then that typically you will always apply this method to standardized data. To take out the different kinds of units that maybe some kind of variables are measured in. So you will typically always apply this to standardized data. I will actually do some illustrative examples that are not with standardized data. But again, you typically will always apply this to standardized data. Please remember that before you do any kind of project, before you do any kind of test. And outside this class, if you apply this method, please remember that too. There are 2 main functions in R that does this, or applies the K nearest neighbor method. One's called KNN, and one's called KNN.CB. These are from the class package, class standing for classification. This package is automatically installed into R. Brian Ripley, who's the author of the LDA and QDA functions, also authored these functions. KNN basically applies resubstitution. KNN.CV applies cross-validation. So what I mean by resubstitution, or let's talk about cross-validation first. We were basically applying cross-validation when we were talking about this plot. That with this red dot, we looked at its nearest neighbors to come up with a classification point. Now let's suppose that we happen to know that this red dot actually comes from population number 1. What resubstitution would do is actually take that into account. So if I went to 3 nearest neighbors in that particular case, the first nearest neighbor would be the red dot. The second nearest neighbor would be the 1. The third nearest neighbor would be the 2. And we will classify that observation to population 1. So you can see the bias that can be induced by using resubstitution. So you might be thinking, well, why am I showing you then, why am I going to talk about the KNN? Why am I going to talk about the KNN function? Well, it's a good function to use if you want to, let's say, apply these methods then to like a validation data set. So that's why we need to know how KNN works as well. Okay, so let's look at a very simple data set to make sure you're following how this is done. And also this would be a very helpful data set to see how ties are handled. So the data set is simply called 4 observations because there are just 4 observations. A plot of the observations shown on page 4. I do this plot using just the standard methods that we've done before, so I'm not going to go over the direct code for it. But what you can see here is that we have 2 observations from population number 1, observation 1 and 2. 2 observations from population number 2, observations 3 and 4. Notice how they are spaced. They are, for example, observation 1 is an equal distance from observation 2 and also from observation number 3. I did this on purpose so that we can see how ties are handled. Okay. Also, what I did was I actually found then the distances. So, again, from the cluster analysis section, remember the dist function itself. And you can see the distance at observation number 1 is from observation 2 and 3 is a distance of 1. This is Euclidean distances. We will only use Euclidean distances for this example. We will not standardize. Okay, so let's use KNN with k equal 1. Let's take a look at how we can do this. I'm going to jump on over here to my program and get the data into R. And then, since it's in the class package, I have to say library class. To use a KNN function, I need to first specify the argument train. Train stands for training data, like model building data again. And the data is in set 1. The first column is variable 1, the second column is variable 2, the third column is a population number. So I'm going to apply it to set 1 without that third column in there. Then I'm going to ask KNN to classify the observations that are in set 1. Again, think of resubstitution. Again, I remove the third column. The CL argument stands for classification, meaning what are the classifications for in the training data? Well, that happens to be in column 3, the population numbers. I specify my k with a lowercase k, and I'm going to use 1. Prob equal true, print simply the probabilities. If you remember when I had that very simple example earlier, I said the proportion of observations from population 1, proportion of populations from observation number 2 for the nearest neighbors. Well, this will actually calculate these proportions for you. So I am going to now run this, put the results into something called NNC1, and this is what I get. Simply, NNC1 is returned to you simply as a vector. It is actually a factor. And it gives you the ordering for which the observations are classified into. So observations 1 and 2 are classified into population 1. Observations 3 and 4 are classified into population number 2. Okay. Also, we have something here that says prob, that stands for probabilities. These are then the proportions. Also, you see levels. Okay, let's talk about these proportions. Now remember, I have one nearest neighbor. That's what I'm looking at. I'm using resubstitution. I'm getting these proportions of ones. Why am I getting proportions of ones? Because the nearest neighbor is always the observation itself. Yes. So that's why I'm getting these probabilities that are always equal to 1. These probabilities, and I don't like this aspect of this function, these probabilities then always represent then the let's call them proportions. These proportions always represent the proportion of observations from the population from which this observation is classified into. So, for example, let's say that this first proportion was, let's say, 0.8. Okay? What that means is 80% of the observations came from population 1, because that observation was classified in there. It doesn't tell you what the proportion of observations were from population number 2. Now you might be thinking, well, geez, that's easy. I can take 1 minus 0.8 to get 0.2. But what happens if you actually had 3 populations in your data set? Then you will not know what the other proportions were. You only will know the proportion that's the highest, which corresponds to the population from which the observation was classified into. I will have another example of that coming up with the place king data set if that wasn't totally clear. So stay tuned for that. Okay. So, oftentimes whenever we get an object like this from a function, we use the names function on it. And we can see if I say names NNC1, I have null. That's because this is not a list. When we were doing stuff with many of the other functions, such as printcomp, we would have a list in terms of our terminology, a list returned to us. Instead, it's a factor that's returned to us. And so if I say class NNC1, you see it's called a factor. We've talked about factors. Actually, I think it was in the last class. Just a way to represent a categorical variable. And the problem, though, is that you see that in this NNC1, we have these classifications, but we also have these probabilities. And maybe you might want to access those probabilities somehow. How do you actually access them? And we have to use some coding that we haven't seen before. There is a function called attributes in R. So if I come back up here again, you see this says ATTR. This vector, the 1, 1, 2, 2, has an attribute called probability. And you can see the attributes of a corresponding vector by saying attributes, that vector. And we see we have the 2 possible levels. We have the class. And then we also have prob. So if I wanted to actually access those posterior probabilities, if I want to actually access those proportions, I can do that by saying attributes NNC1 $prob. That's how you do it. Coding's kind of weird, but this is how you do it. I think the coding's a little bit weird because this function was probably written, I would imagine, let's say in the early 1990s, before this would have been written for the S+ software package, and this was before conventional programming techniques came out. Let's say for R, because R didn't exist at the time. Okay, let's move on. Just close that out. And so, you can easily then put all the observations together with the actual classification. It's not too difficult. And so that's what I did there. This could be useful to see by observation which the classifications are. So we already talked about the first question. And we've kind of already addressed in the second question, why will k equal 1 always result in perfect accuracy with k and n? Because you're using resubstitution when you're trying to classify the original data itself. Okay, so let's look at what happens then with k equal 2, 3, and 4. And this is especially will be helpful to us to understand how ties are handled. Okay, so I'm going to create an object called NNC2. I'm going to use exactly the same code as before, but now I have k equal 2 in there. NNC2 has these classifications. Notice it gets everything right. And observations 1 and 2 from population 1, observations 3 and 4 from population 2, so everything's right. Here are these proportions. 0.6667 for the first observation. So the proportion of observations from population number 1 was 0.6667. K equals 2. How can you get 2/3 if k was equal to 2? This is now how ties are handled. Let me go back to the plot. Okay, so let me actually do some erasing too. So the first nearest neighbor for observation 1 is observation 1. So I'm going to put a 1 there. That is supposedly a 1. Anyway, the second nearest neighbor is what?
3.
It's a tie. So this is the second nearest neighbor, and this is the second nearest neighbor. Okay. So what R does with k and n is it includes all ties then in the overall number of nearest neighbors looking at. So instead of just looking at 2, what ends up happening is that 3 nearest neighbors are used, and we can see that there are 2 observations for population 1. So 2 divided by 3 is 0.6667 if you round. So that's how this is working. Any questions about that? And because of how I arranged all the data, you notice we get the 2/3 for all those probabilities. Well, let's look at now using k equal 3. So I have k equal 3 there. Notice it gets everything right. And notice my proportions. 2/3 always. Well, after what we just got done talking about, hopefully that makes sense. So the 3 nearest neighbors to observation number 1. Well, obviously observation number 1. And then we have a tie for the second nearest neighbor. But in total, then that means that we have 3 neighbors there. And so those 3 neighbors then are used to come up with these proportions. It would not go to observation number 4, because then it says that now you have 4 neighbors.
So if that's true, why isn't it 2/3?
It is 2/3. It is
With the k equals 4? Oh,
with k equal 3. Sorry. Okay, now for k equal 4 then, what this basically means is use all 4 observations, right? We have 2 observations for population 1, we have 2 observations for population number 2, and so we're always going to have 0.5 as the proportions. Well, what does R do then to decide the classifications? It chooses them at random. So, for observation number 1, it chose population 1. It does it at random. So let's say if I ran this code again, would I be guaranteed to get exactly the same answer? No. This is why whenever you use KNN or even KNN.CV, you should always set a seed number before you run it so that you can reproduce the exact results. Again, let me emphasize that. Always use a seed number before you run these functions. I didn't here because I'm just demonstrating how these functions work at this time. Okay, so that takes us to page 7. So let's look at how KNN.CV works. Very simple. We're going to use one nearest neighbor. For the train argument, again, I put in my data set, excluding the population number. Obviously, that's a place where you can make an easy error, especially like on a test, that you forget to exclude the population number. CL stands for what are the actual classifications. Again, that would be then column 3 in my data. I'm going to use k equal 1. I'm going to say prob equal true. So notice the only thing that we don't have is the test argument. That's because we're using cross-validation. We're trying to classify the, always in this case, you would be trying to classify the observations in the data set itself. Okay. So, I want to do a split screen here. We need to go back and forth between the plots, or between the plot. Oops. Okay, so let's look at observation number 1. It is classified into population number 1. Notice the corresponding probability, 0.5. How did that happen? Well, let's look at the plot. Do some erasing. How did that happen? Okay, so we're looking at the nearest neighbor to observation number 1. We can see it's a tie between observation 2 and 3. R then includes all ties in making in coming up with these proportions. So we can see 0.5 for population 1, 0.5 for population number 2. It's again we have an equal value there. So how does R then choose population and population? How does it choose between population 1 and population 2? It chooses at random. So we have a number of things that were combined there. We had a tie for the distances, so all the distances were included, and then the proportions were a tie, and so because of that, R randomly picks a population. And the same thing happens then for all the observations, based upon how I arranged everything. Any questions? So let's look at 2 nearest neighbors. So everything's exactly the same here. Notice the classifications were exactly the same too. I actually did set a seed number in my program. And we get these proportions of 0.5. Why did I get exactly the same thing? Because I was essentially doing k equal 2 before with k equal 1, right? Because of those ties. Let's look at k equal 3. Now, we'll look at observation 1. So the nearest neighbor, we have a tie for shoot. Obviously, the nearest neighbor and the next nearest neighbor would be k equal 2, observation 2 and 3. There's a tie. And then the third nearest neighbor would be observation 4. Notice 2/3 of the observations are for population 2. 1/3 is from population 1, so this is classified as coming from population number 2. And in fact, this happens for every single observation, so all of the observations are misclassified because of how all that is arranged. What if you use k equal 4? Could you do it?
There are no more observations.
Yeah, there were no more observations because we're using cross-validation, which says, okay, you're not using the observation of interest itself to classify it, and that means that there are only 3 observations left. If you say k equal 4, you get a syntax error. Or I shouldn't necessarily say syntax error, but you get an error message. Okay, so that's how it works. Again, it's not difficult, but you do need to understand how the ties are handled. So that takes us to page 9. Well, how do we choose k? Obviously, this is very important. Well, one thing that you might be able to do, again, you might, is to do some kind of plot of the data, maybe just a simple scatter plot or actual scatter plot of the principal component scores, and look at that. And maybe a particular value of k would make sense to you. More often, that's not going to be helpful. And so instead, what you might simply do is try a whole bunch of values of k, and the value of k that would be best is the one that has the highest classification accuracy. That's it. Now, obviously, if you have a data set of 1 million in size, do you want to do k equal 1 to 1 million? No. So, I mean, you have to draw the limit someplace. And so, what I'm going to show you shortly with the place kicking data set, I said, well, why don't we just go up to k equal 10 and try that. One of the nice things then that you can do to make you feel better about whatever you choose as an upper limit for k is look at a plot of the results. And if you see that as k is increasing, you keep on getting better and better and better accuracy, well, maybe you should use a higher value of k. If you're seeing that you are not really gaining anything by continuing to increase k, well, then you feel better about yourself, and you feel confident that if you choose up to k equal 10, you're okay. You're not missing anything. Okay, so let's look at how we would choose a value of k with respect to the place-kicking data set and see overall how this method works with the place-kicking data set. To begin with, though, I'm just going to use k equal 1 so that we can see how things are working with the place-kicking data set. And because I wrote my function summarize.class so nicely, we can use this function then to help us determine what is the correct classification rates. So with my data, then, I'm going to read in my place-kick data set and my validation data set. And put a star here. I also standardize my data. Both data sets, place-kick and validation. Notice when I standardize it, I remove column 9 because that actually tells me was the place-kick a success or a failure. This is my population number column. That's why I removed it. Okay. The first thing I'm going to do is use the KNN function. Now, I'm not going to try to classify the observations in the place-kick data set itself. Instead, I'm going to use it with the validation data set. So I say, so first of all, I set a seed number so I can reproduce my results. My training data set, is in Z, which is my standardized values for the place kick data frame. And then my test data set is Z.V, which is my standardized values from the validation data set. CL, what are my original classifications? That's in the 9th column of my place kick data set. Notice I'm not using validation there. I'm using the place kick data set. I'm going to say K equal 1, prob equal true. And this is what I get. So for example, for the first observation, it's classified as a success. Second observation is classified as a success. Third observation is classified as a failure. So essentially what's happening is with the validation data set itself, and I should make sure this is clear, these are classifications for the validation data set. So there will be like 300 and some ones and zeros there. Classifications for the validation data set. So what it does is for the validation data set, it takes observation 1. It calculates all distances between observation 1 and the validation data set and the 1,400 and some observations from the place kick data set. And uses that to see which observation is it closest to. So it finds it, sees what the corresponding population number is, and then makes the assignment. Any questions about that? I wouldn't necessarily call it cross-validation because you're not performing on the data set that you're actually classifying. You're not using those to find the nearest neighbors.
Yeah, but I mean, so when Kate is one, it's not including stuff, just like when
I think you need to think of it from a different perspective. Let's say that we have let's think of it this way. So we have this training data set called place kick, okay? And let's say that we want to go out and kick a new place kick from 40 yards, no wind, no pressure, and so on. And before you do that place kick, you want to be able to decide, is this going to be a success or failure? So what you do is you compare that potential observation, you could say, to then what you've already observed to decide what was most similar to it.
that makes sense because we're not including the application of this.
The validation, yeah. Yeah, so yeah, notice here that it's K and N function. We never ever tell it what the original classifications were for the validation data set. We don't need to. Was there a question?
Yeah, so isn't this kind of analogous to the nearest neighbor cluster analysis where we catch it at a point in time after we've done all of our training observations? And now we're going to start adding in our validation observations?
It can be, yeah. You see some similarities because obviously we're using these distances, and that's what we were often doing with the clustering. It is somewhat different to some respect because obviously in cluster analysis we didn't know what the groupings were, but there are some similarities. Yes. The clustering methods. Cluster analysis. We were only looking at nonparametric. Okay, so also, let's do cross-validation now on the original data. So I'm going to, again, set a seed number. Now, I guess also let's talk about this. After this, if you were to, let's say, outside of this class, you had a data set you wanted to apply nearest neighbor classification to, would you use my seed numbers? I would hope not. Pick a different seed number, okay? You should think back to your Stat 801 days, or even a class before that, where you talked about random number generation and and picking seed numbers. Don't always. This is not a magical seed number here. Okay, pick a different seed number. If you need help on understanding how to pick seed numbers, talk to me after class. Anyway, okay, so. Training data set is in Z. The classifications are, of course, in column 9 of the place kick data set. K equal 1, prob equal true. And as you would Excuse me. And here are the actual classifications. Now, in this particular case, since I am classifying the stuff that's in PlaceKick itself, I have 1,400 and I think it's 25 ones and zeros in this vector nnc1.cv. Let's look at how well these classifications are done. So here's my summarize.class function that we've seen previously. And simply I do this. Summarize.class. My original classifications for the validation data set are in column 9 of valid. And then the actual classifications are in NNC1. I run the function with it, and this is what I get. So 26 times I had an observed failure, and it was classified correctly. 235 times I had a success, and it was classified correctly. 12 times I made an error in terms of it was a failure but classified as a success. 9 times I had a success that was misclassified as a failure. You can see these proportions too. You know, I'm always very concerned about, I guess it depends on how you look at it. I'm always concerned about the diagonal. I want to get those numbers that I have circled there as large as possible because that represents my correct classification rate. My overall classification rate is 92%. So that's for the validation data set. For the using cross-validation with the original data set, you have a similar set of results. My overall correct classification rate is about 83%. Okay, let's discuss this. So typically, with your validation data set, it will always have a lower classification accuracy than when you do cross-validation. Typically, validation will be lower than cross-validation. In this case, we have the opposite happening. I was kind of surprised to see that. What I think is happening is this. Remember with our original PlaceKick data set, we only had 11% of the observations were failures, 89% were successes. The same thing happens with the validation data set. But obviously with the validation data set, we have a lot lower number of overall observations. So in fact, we only have 38 failures in the validation data set in comparison to 244 successes. So what I'm thinking is happening here, since we have a higher classification accuracy with the validation, is that we are just seeing some of the variation in our data. In that, you know, we have so many, we have such a low number of failures to begin with, and we're just seeing some variation that's happening here due to the low numbers. That if I were to go out and let's say maybe get another data set, this might not happen. That's my theory. I don't know if there's really a truly an answer, a direct answer for that. I'm sorry, not direct answer. I don't think that there's necessarily a correct answer that's readily available, but that's what I think is happening.
So do you believe the cross-validation one more than you believe?
In this case, I do. In this case, I do. Okay, so this might be a good place to stop because now we're going to apply the same idea from KCAL 1 to KCAL 10. If you're using a for loop, it might take probably about 5 minutes to go through this for loop. But you know, if you want to look ahead to page 13, and you see some plots of the actual accuracy of these methods. And from those plots, we're going to make a decision about what value we should choose for K. So, are there any questions? And that's it for today.